All right, so continuing with our thermodynamics discussion, we have to sort of first set some definitions, okay, and sort of establish our vocabulary for the things that we're going to be talking about. And um, when we go to analyze a specific, say a thermodynamic device or thermodynamics, do some sort of analysis, we have to sort of first establish what it is we're trying to analyze, okay? And typically what'll happen is we draw a boundary around the thing that we're interested in. That thing, whatever it is that we're interested in, is called a system. We call it a system, okay? In sort of general terms. That system is going to have properties. It could have, the total mass of the system, say, or the total energy in the system. And the mass and energy can only enter or leave the system by crossing the boundary. Okay, so you know, we've established the region of space or the device it is that we're talking about, and we've distinguished between it and what we call the surroundings, which is everything else. So we divide the universe into two parts: the system that we're interested in and the surroundings. That those two parts are partitioned using a boundary, and then mass and energy can cross the boundary. They have to cross the boundary in order to enter or leave the system. All right. So a system has properties such as pressure, temperature, volume, density, energy, specific volume, specific energy, and I'll get into details of exactly what that means here in a minute. The collection of these properties is called the state. Okay, so the state of the system is the collection of properties which define the system that we're interested in. All right. So properties are the sort of variables which, well, variables which define the state. Okay, and then the state is the entire collection of these variables, of the properties. Okay. And properties come in a couple different forms. They come in what's called an extensive property. Extensive. And these are dependent on the size or the mass of the system. Some examples would be, say, the total volume of the system, the total energy of the system, the total mass of the system. There's different forms of energy, and you'll become accustomed to them here shortly. But like, we use the uppercase letter U for the internal energy, what's called internal energy, and then the total kinetic energy of a system. So these all depend on the amount of stuff in the system. The total volume is kind of obvious. The total energy, if I expand the boundary to include the system and then a little bit more, the total energy is likely to go up. right? And so these depend on the actual size. Notice they all get capital letters except for the special case of mass. It's just always given in lowercase m. But for the most part, extensive properties are the symbols used to define extensive properties are given uppercase letters. Okay. Then you have intensive properties. And these are independent. On the size or mass of the system. Examples could be, say, density, pressure, temperature, things like that. So the temperature, another way of saying, of differentiating between extensive and intensive properties, are that extensive properties or intensive properties can be defined at a point. So I can vary the size of the system all the way down to a single point, and the concept of pressure would still have a meaning. The concept of temperature would still have a meaning. But the concept of volume would not. The concept of total energy of a point does not make sense, nor does the mass of a point or any of these other properties. So intensive properties are defined at a point. That's the way I like to think about them. Okay. Now I can take an extensive property, and if I express it in terms of per unit mass, if I express it in a per unit mass on a per unit mass basis, they become intensive properties. So a specific property is essentially an extensive property per unit mass. Okay, and so that might be, if I have the total volume and I divide it by the total mass, I get an average property. I get an average value of what's called the specific volume. Okay, so this is total volume, and this is specific volume. Generally given with a lowercase v. So we've got uppercase V for the extensive property, lowercase v for the specific property. So the same thing goes for energy. So I have the total energy divided by the total mass in the limit, at least. And this is given by the specific energy. So if I have an extensive property per unit mass, I get an intensive property, which is, well, I get a specific property. Okay, so it just gets a qualifier specific and gets expressed with a lowercase letter. Okay, and the thing about specific properties, they are intensive. So if I take an extensive property, express it in a per unit mass basis, they become intensive properties. So specific properties are intensive. Okay. All right. So the state postulate. And so this is an important definition of how we fix the state. Okay. And so So it's a postulate, so it's sort of one of the entering assumptions into our whole analysis or our whole theory. All right. So what it says is that if I give you two independent intensive properties, I fix the state. So the two words that are doing all the work here are independent and intensive. So we're going to get into situations later on where, say, you can have two intensive properties and they won't necessarily be independent of one another. Like, I can't change one without changing the other. An independent one, like independent properties, I can change without changing the other. Like, I can keep the specific volume the same while changing the energy somehow. By maybe I add heat or something like that. Okay, so there's never a case where these two properties are not independent. But there will be some cases where the pressure and temperature are not independent. And we're going to get into some detail here later. But what the state postulate is saying is that if I have two intensive properties, say pressure and the specific volume, they're intensive properties. They can be defined at a point. If I give you those two, you necessarily know all of these other variables. You know all of the other intensive properties, okay? You know the temperature. If I give you the pressure and the specific volume, and I tell you what substance is in the system, you're going to know the temperature, you're going to know the density, you're going to know the specific energy. I'll have to tell you the size of the system in order for you to know things like the volume, the total volume, and the total energy, and stuff like that. But this, in order to fix the state, I just need to give you two independent intensive properties. Okay, and then maybe some information about the size. All right, and so because I only need two independent properties, I can plot the state in diagrams like this. So say I have the pressure and the specific volume. I can plot every point on this plot constitutes a state of the system. All right. So this point is specifying the pressure and the specific volume, but because of the state postulate, I know the pressure and specific volume, but I also know all of these other quantities. Okay, so associated with this point is the entire state of the system. And I usually label a state with like a number, circled number, okay? So here, these are two states. And a process is a path, can be thought of as a path in this, on this diagram, which defines the method by which I went from state 1 to state 2. Okay? So this path is known as a process. Okay? Now, because I'm free to choose which two independent intensive properties I use. So say it's more convenient for me to express this process in terms of the temperature and specific energy, you know, or pick your, I could say temperature and pressure if those two happen to be independent. Any two intensive independent properties I can use to express the same diagram. So I can express this exact same process in this diagram, and it may look something like this. So here's state 1 expressed in terms of the temperature and specific energy. Here's state 1 expressed in terms of the pressure and specific volume. So here's state one, here's state one. It's the exact same state, just expressed in terms of two different, an exchange between two different variables. Okay. So here's the process expressed on a temperature specific energy diagram, and it goes from state 1 to state 2. So this is the same process. And this is the same process in terms of pressure and specific volume. Okay. And I can, I can take these processes and I can chain them together, right? So every point in this diagram constitutes a state of our system. Every one of these lines constitutes a process. And if they form a closed loop like this is called a cycle. So this whole thing is called a cycle. The collection of these four processes. So maybe you would call it process 1, 2, process 2, 3, so on, and then 3, 4, 4, 1, and the collection of these four processes is going to be known as a cycle. Okay, and then we're going to get into the specifics as to what different processes look on plotted against different variables here in the future. So